also it's the kind of things that are of interest to absolutely no one these days. There are no one except me, so I'm interested in them. So, but I think this, I'm interested in designing languages and designing programming methodologies for reliable programming, and this used to be of interest to some people, but I mean, no one cares anymore. I mean, in terms of software, what counts is how quickly you deploy the software. In terms of programming languages, it's a matter of fancy language constructs, say whether you understand their semantics or not. So this is, yeah, totally uninteresting, but still, as it's of interest to me, I will describe it. So what I'm going to do to use as a conduit, at least to start, is to go more or less through the structure of the paper that I'm writing at the moment, that I was asked to write. It's not finished. In any case, I don't think I can publish it, so it's going to end up on archive or something like this. I don't think any journal will accept that paper. But again, it's of interest to me. So this is basically a selfish presentation. It's a presentation for myself, and I don't expect anyone to be actually interested. So it's called The Essence of Object Technology, and what I'm trying to do is to go back to what is really critical in object technology. Object technology, as it says here, rules the world. And if you look at things like the TIOBE index, which is a site which tracks the usage of programming languages, much of the world today uses languages that are labeled as object-oriented, languages like Java, JavaScript, C#. I've even heard that some people consider Python to be object-oriented, C++, of course. So it would seem that, especially for those of us who remember when we were pushing object-oriented ideas against a lot of resistance and people were dismissing them as academic, it would seem that we have kind of won the battle. But in fact, if you look at what people call object-oriented programming and object-oriented languages, my view, which I'm going to try to justify, is that it's actually a toned down, a somewhat distorted version of object technology that is being applied on a large scale, which really misses on some of the major benefits that are advertised for object technology, such as, in particular, the three main ones, which are extendability, the ease of changing your software, reusability, the ease of taking advantage of software that you have written before in order to include it in new developments, and reliability, which is the ability to write software that works and that performs according to specification. So if you don't apply the object-oriented ideas fully and seriously and professionally, then you can still get some advantages, of course, but object technology doesn't really deliver on its promises. So I'm going to try to explain some of this, and of course I have an agenda. I cannot say a hidden agenda because it's not hidden at all, but what I've been doing for a long time now is to put everything I understand, everything I know into the design of an object-oriented language, method, environment, library, and tool set, ID, which is Eiffel, and of course everything that I describe. If I criticize some of its application to other object-oriented languages, it's because I think it's done rightly in Eiffel. It's actually the other way around. Eiffel was designed to be a proper implementation of object-oriented ideas, and I've always been flabbergasted to see how poor the huge misunderstandings that have guided the design of other object-oriented approaches. So I'm going to, you know, as I said, this is a very messy presentation, but still it has some kind of implicit structure in it. So what I'm going to do, initially I will start by following this paper. The paper is in progress, so I'll use the parts that I have that are written, and for the parts that are not yet written, I will resort to some slides that I have. So I'm going to start by recalling what I believe are the basic concepts of object technology, of object-oriented technology. For the purposes of the paper I introduced, I identified 10 of them. And then I will, a little later, but let me show it to you already, just as a preview of the structure. Yeah, so then I'll introduce a bit of mathematics. I'll explain this in a minute. But after the mathematics, I'll go into some of the misconceptions that I believe exist in dominant object-oriented languages, poor implementation of dynamic binding, overloading, which is an absolute catastrophe, which destroys the entire object-oriented edifice, and it loses all the simplicity, the mess with constructors, the poor understanding of inheritance, and in particular multiple inheritance, the horrendous idea of interfaces as they exist in say Java or C#, and then I'll talk a little bit. It's not written in the paper yet about. I don't think I'll talk about static typing because I don't have the time, but I'll say a few words if time permits on about voice safety. So this I'll skip. But and I'll say a few words on something which is not here, which is concurrency, as well as design by contract. So let me come back to the beginning. If I can, yeah. So what's object-oriented technology? So here, I mean, there are lots of definitions of object technology, including by me. In the end, I'm concentrating here on 10 concepts. It's a little too many, I would like to say, to be able to say there's like two or three things. You know, many of the important things in science are defined at the root by a very small number of concepts, you know, 2 or 3. But here, in order to avoid losing something important, I've not really at this point been able to focus on less than 10. So 3 dynamic concepts, so they have to do with execution or with modeling. It doesn't just have to be with for software programs. Then 3 static concepts, which have to do with this static description of these dynamic concepts. Then 1 really fundamental architectural concept, and then 3 programming concepts. So the others, the first 7, are really independent of software. They are typically applied to software, but they can be applied to the modeling of systems of many different kinds. The last 3 are really specific to software. So let me start with the dynamic concepts. It's kind of strange, but because this is not emphasized so much, you know, you have the kind of standard stable definition of classes, encapsulations, and inheritance. You know, where if I ask a candidate or a student what is object technology, that's what they're going to say. They don't really understand what it means, but they've kind of learned this by rote, classes, encapsulation, inheritance. It doesn't really mean very much. So, but still, it doesn't encompass the runtime structure at all. And in fact, without having, after all, in object-oriented technology, it's about objects. You could say it's not about objects, it's about classes, but how can you define classes without defining objects first? So I kind of resisted this for a long time. And if you look at some of my writings, they typically tend to start with classes, but in reality, it's not so stupid to start with objects. So we have fields. So fields, they're elementary values. So they can be things like integers and such, or Booleans, but they can also be references. Okay, so there's this notion that in object-oriented databases, people pay a lot of attention to this. It's object, they call it object identity. You know, you can have values that identify objects. This is very important. So we have fields, maybe I should have put it in a, no, this is the right order, sorry. Then you have an object, which is a finite collection of fields. And then we have one of the possible kinds of field, a reference, as illustrated by two examples in the figure, which is a kind of field that uniquely identifies an object. So these are the runtime, the dynamic concepts. Then we have static concepts, and they fit here in like 10 lines, but they're absolutely fundamental. So the class, the notion of class, client, and inheritance. So class is a description of a set of objects. At this point, we could call it type. It's the same thing at this level, at least. So a class is the description of a set of objects that have the same operations applicable to them, commands and queries. Then we have two relations between classes, and it's really important to distinguish between these two. UML, I think, kind of messed up here by focusing too much at the implementation level, rather than the conceptual level. At the conceptual level, we have client and inheritance. Client exists between classes when one of them is able for its instances, its objects, to use operations on instances of another, or the same class on the sole basis of their specification. And then inheritance is another relation between classes, which is the specialization relation. And there's not that much there seems to be not that much in what I just said, but in fact, if you take the consequences, it's quite important. So for example, I don't know why C++ started to introduce this idea that of protected, the idea that you can hide operations or members or whatever from your descendants. It makes absolutely no sense at all, because inheritance is a specialization relation. So if you inherit from another class, you inherit everything. Client, of course, has information. So next comes one fundamental architectural context, which is expressed here, which is the fact that we solve two problems with one structure. So one problem is the type mechanism. In every approach to system modeling and to programming in particular, we are going to have a notion of type. What type system do we have? And then so this is like more a dynamic notion, and then we need, in any approach, a notion of module. That is to say, we need to cut our models into pieces, or our programs, if they are programs, into pieces. So we have modules. And a module is basically an encapsulation, a grouping of operations, of services that we offer to the rest of the world. So the beautiful, elegant, and I would say brilliant intuition of the people who came up with Simula 67, the first object-oriented language, was to say, even though they didn't express it in exactly that way, we're going to merge these two concepts. The module concept is going to be the type concept, and the basis for the type system is going to be the same, the notion of class. So class is the fusion, the merging of the notion of module and the notion of type. How can we merge two notions that seem so different? One which is a description of values, types, one which is completely static and structural, which is the module. Well, the trick, this brilliant intuition of Christian Nygaard and Ole Johan Dahl that I mentioned, the creators of Simula 67, was that the fusion comes from saying that the services of a class are viewed as a module. So a module offers some services. Well, what are these services? They're precisely operations on instances of the class viewed as a type. And it takes many months or years or maybe a lifetime to understand this, but it's really very deep. And I think we can be grateful to these two Norwegian guys for intuiting this powerful idea. And then we have, if we are not just talking about programming, about system modeling in general, but about programming, we have three programming concepts: typing, polymorphism, and dynamic binding. So every entity of the program, so here I'm talking about a program text, can take on values of specific types. So this is true of any programming language. You take a non-completely so-called untyped programming language like Python, this sentence still remains applicable, because when you have an entity of a program is going to take values of certain types, be they strings or integers or wherever else. However, what is going to work with object-oriented programming is static typing, meaning that there is some indication in a program text of the possible values. Then we have polymorphism, which says that this typing policy is actually flexible. You know, it's like in Pascal, where or you know, very strictly statically typed languages, or Ada, not today's Ada, but previous versions of Ada, where if you declare something of type polygon, well, it has to be exactly of type polygon. It cannot be a rectangle or a triangle or something. So polymorphism gives us some flexibility thanks to inheritance, and then dynamic binding, which is this other beautiful mechanism which says that if I have an operation, or also known as a feature, which has several variants in the program, and that operation is
Professor Meyer, your microphone. Could you please check your microphone? It seems your microphone has been switched off.
So sorry for that. When I become too excited, I start touching. So it's one of these Jabra microphones. I'm not used to it. I borrowed it from a colleague, and I guess if you touch it, it thinks that you want to turn it off. Thanks for telling me. I appreciate it. Right. So dynamic binding is this also very elegant mechanism, which in the context of polymorphism says that when an operation has several variants, then it goes beyond information hiding and applies the proper operation. And information hiding says, if I'm calling the operation perimeter on a closed figure, I don't need to know how perimeter is implemented. So I rely on the API. I rely on the interface. So that's you know, David Parnas, 1972. It's a very powerful concept. And then there's the next step, which actually was invited 5 years before, you know, by Simula 67, which says not only that, not only do I not know how a perimeter is implemented, but perimeter might have many different implementations, or for general polygons, for rectangles, for triangles, for squares, and so on. So I don't even know which of these versions is going to be applied. It kind of magically, automagically, as people say, adapts to the type. All this, of course, guided by a specification, which I would also call a contract, but that's for later. Okay, so these to me are the 10 fundamental concepts. You know, you could say it's 9, you could say it's 11, you probably could add a couple. It's important in science to start with small definitions. If you start defining a concept by 50 different properties, then there's something wrong. So before I go to the applications, let me mention a couple of mathematical concepts which I find useful to talk about about programming in general. Actually, not just object-oriented programming. So these are things that you've all known since kindergarten, and maybe before. Let me just introduce the notations. Right? So you know about Cartesian product. It's a set of pairs. A relation. What's a relation? So formally, a relation is over A and B. It's a subset of the power set of A Cartesian product B. You can see that there are typos in this text. It's not final yet. There's a space missing. So, for example, this is a relation, right? The relation successor, pictured here. 1 is the successor of 0, 2 is the successor of 1. And I'm only looking at it over this set of 0, 1, 2. So relation has a domain and a range. the domain is the set of values for which it's defined, and the range is set of values for which it gives, which are the set of values which are the result of the relation. So this particular relation is partial because it doesn't have in its domain, it doesn't have two. Okay? If we took the successor function for all of all integers, then it would be total. A relation is a function if for any element of the source set, it contains at most one pair, starting with that element. Okay? So for example, successor is a function because for 0 there is 1, for 1 there is 1 successor, and for 2 there is none. So at most one. On the other hand, if I take less than or equal, which is a relation, it's not a function because, for example, it has 2, 2, and 2, 3 over integers. And then the function is total if it's always defined. A little bit more mathematical. I think I'm going to skip this discussion of why Cartesian product is bad for your health, but let me just introduce. Actually, let me explain why a Cartesian product is bad for your health. I mean, it may not have an immediate impact on the rest of the discussion, but as part of preaching to the world, I think I should continue to slander a Cartesian product, which has a really bad influence on youth. So the problem, and old age actually as well. So the problem with Cartesian product is that you have to say exactly what the elements are. So for example, you say a book is a string, the author, another string, the title, and an integer, which is the publication date, which is fine. You can also write you can put it as a C record, a C structure, or Pascal record. What's bad about it is that, of course, at some point you're going to want to have something else, like an ISBN number, and then you have to redo everything, which is exactly what object-oriented programming is against. But here I'm talking about mathematical modeling. So a better solution for this kind of situation is to use this, to use a finite mapping. So here, if I use this notation, which is very much like a Pascal record or a C structure, it doesn't mean a Cartesian product. It's in one-to-one correspondence. Okay, but what it really means is a function which, for author, yields the corresponding value for title and for year. So it's a partial function defined for 3 values. And so if we know exactly the contents, it's in one-to-one correspondence with the Cartesian product definition. But the big difference is that we can add elements easily. Second important notion, currying. So currying means that you take people who do functional programming, of course, are very familiar with it. It means that you take a 2-argument function, and again, we don't like Cartesian product too much, so we replace it by a 1-argument function, which yields a function. And this is essentially what object-oriented programming is, because we have this notion of class, so we always apply an operation to one object. So even if we have an operation that in some other approach would take several arguments, we pretend that it's an operation with one argument, the target of the call. So that's why we have this object-oriented notation, target dot operation. There's always a target, right? Which again, it has many consequences. Last mathematical concept, it's something that I don't know why it's not better known, because whenever I try to do any mathematical modeling of programming concepts, I immediately hit upon its necessity, but it's not so well known. There are other notations for it. I like to use this notation here with a union that with a bar that leans towards the right. It could lean towards the left. It's just a matter of convention. The problem is this. Let's assume that I have 2 functions, A0, B1, and A1. Okay, so they are functions because for each one of them satisfies the function property that for any element there's at most one result. But if I take the union, which of course I can because these are sets of pairs, so you can apply the union, what we get is a relation of this one here, but it's not a function because it gives 2 distinct values for A, 0 and 1. Okay? And we often have to do this. We will often need to combine two functions, and we want to get a function as a result. So this overriding union operator simply means, well, let's take a union, and in the case of conflict, let's take the value from the second operand. It's a matter of convention. We could take the first operand. But it's kind of nice to take the second operand to say the second, we override f by g. This is basically what it is. Okay, so now I come to misconceptions in dominant object-oriented languages. The point about dynamic binding, it's most, I mean, recent object-oriented languages tend to get it right, Java and C#, so it's not such a big deal. It's really C++, which was completely messing up the picture here by essentially offering a choice between static binding and dynamic binding, and in fact offering static binding as the default. You get dynamic binding for virtual functions, but not for others. So this is absolutely atrocious, in particular because, or essentially because, static binding is never correct. Let me correct this. Static binding is correct only if it has the same effect as dynamic binding. But when you apply an operation to an object, you want the right version of the operation to be applied, not some version which happened to be in an ancestor class. So I should have included a picture here, but let's assume that we have in the graphic system a class box, okay, and a descendant class labeled box. So it has the box, and then on top of that it has a label. So it's going to redefine to the text, the label. And so if you have a polymorphic variable figure, which is declared as a box, but dynamically denotes an instance of labeled box, if you apply static binding, you will get a completely garbled display because you use the wrong version. So on the other hand, this is kind of a done deal in the sense that starting with Java, later object-oriented languages did the right thing, which is to always apply dynamic binding, which is of course the case with Eiffel. Now, in some cases, you can optimize. So there's a compiler optimization to realize that a routine is never redefined, so static binding is okay, or that a particular variable in a particular call is not polymorphic. So then the compiler has to be smart enough to apply static binding. But conceptually, it's always dynamic binding. So there's something worse because it is reproduced in languages, in recent languages, and it really, as I already mentioned, it messes up the whole picture in a much worse way than most people realize. People typically say, okay, maybe we don't need overloading, but it's okay. It's just one more thing that we have. If we don't want to use it, we don't. But in fact, that doesn't work. It just messes up the entire object-oriented edifice. So in languages that were not object-oriented, like Ada in its form until a few years ago, someone had the clever idea to introduce overloading to essentially make the programmer's life a bit easier by making it possible to reuse the same name for different routines which are of a similar purpose. So that's in a non-object-oriented context. So you could have a procedure to display a box, and then you can have a procedure to display a label box, and why not call them the same? I would be against this anyway. I mean, I think it's actually bad programming style, because if you have different operations, you should invent the different names. But for some reason, it was considered a convenience, and in non-object-oriented context, it's kind of harmless. It's not very useful, but it's harmless. Now, of course, one of the reasons we don't need it in object-oriented programming is that we have a much more interesting form of overloading. This form of overloading that is here on the picture at the top is static overloading. That is to say, it has the same name for different things, but the compiler can statically disambiguate this. So if I'm the compiler, if I'm a careful human reader, I know exactly for each call which version of display is going to be used because it depends on the type of the arguments. Okay? So it's completely static. The dynamic binding is much more exciting because, as I said earlier, it's information hiding taken to the next step. Because if I see a b.display, where b is a polymorphic variable, I do not know at runtime, at compile time, which version of display is going to be used, and it's good for me. Okay, that I don't know, because it means that it's going to be the right version determined automatically at runtime. So this is much more powerful. But unfortunately, C++ decided to keep this notion of overloading together with some version of dynamic binding, and this convention was kept by Java and C# and subsequent languages. And the problem is that it messes up the beauty and simplicity of the notion of class. So a class defines, in a proper setup, it defines a mapping from names to operations. This symbol here was in this section that I covered briefly. It simply means a finite function. Okay, so it's a function from names to operations, but it's a function with a finite domain, because in the class, of course, you only have a finite set of names. So the class, I'm sorry, let me start again. In a class, you only have a finite set of names or function and member names. So the class defines a mapping from names to operations, but this mapping is finite, which is what this double bar means here, finite. And when we have overloading, then it becomes much more complicated, because the name, in this case, display, it means different things depending on the arguments. So it's very difficult to specify. I mean, difficult is not the right word. It's very messy, complicated. It's not difficult conceptually. It's just extremely messy and uselessly messy to define it properly in a mathematical way, because basically, as I said, the compiler needs to disambiguate for each call, and so you need first a disambiguation into some kind of internal name, like box, like display box or display label box. Okay, so if you don't have overloading, the programmer is going to invent these names. If you do have overloading, the compiler is going internally to generate these names, and so it becomes much more complicated for no real value. And actually, I think the proof that overloading adds no real value whatsoever is that it already fails for the most obvious of all examples one can think of in terms of overloading. If I want to explain the benefit of overloading to an audience, what I'm going to say is, we have points, or complex numbers, which is the same thing. So when I define a point in a two-dimensional space, or a complex number, I have two ways of doing it: Cartesian coordinates or polar coordinates. So it would be a really good idea to have only one operation set, and then it automatically adapts depending on what you get. Unfortunately, this absolutely trivial example doesn't work, because the signatures happen to be the same. And overloading is based on resolving the ambiguity through different type signatures. So I don't know a way to do this properly. Actually, it's quite catastrophic in Java or C++ because of the notion of constructor, as we are going to see next. So even the most obvious example of where overloading could, in principle, be useful breaks down. And what I would say is, look, names there's no tax on names, right? There's no tax on keystrokes. If you are doing different things, call them differently. If you are doing the same thing with a different semantics, like display in box and display in label box, or in a perimeter in polygon, rectangle, triangle, and so on, yes, by all means, use the same name, because then it's useful. It's different operations with the same semantics as captured by the contract, and then you have dynamic binding. But if it's different things statically, then use different names: set Cartesian, set polar. I mean, it's one of the first rules of programming, that you use different names. So you use good variable names or routine names. Now, this becomes an absolute catastrophe in C++, Java, and so on, because of the bizarre convention for constructors. we need operations to create instances of a class, creation procedures or constructors. So in Eiffel, a constructor is called a creation procedure, and it's a normal procedure of the class, which is just marked as being available to create an object. Okay, so you could have something like this. Yeah, you could make polar. Okay, so if you want to use make polar as a normal procedure, you do this, right? But if you want to create a point by giving us polar coordinates, you say create the same thing. So I think it's clean and simple. Some procedures are marked as usable for creation procedures, which also means, by the way, that if you need to use a procedure both for, say, creating an object, initializing it, and for resetting it, you don't need to declare two different routines, which is what you need to do in C++ or Java or those languages. And code duplication, as David Pandus pointed out many years ago, is the worst enemy of the programming. I would say you never want to have code duplication. Never. I mean, I cannot think of any exception to this rule. I think the way David Pandus put it, or maybe it's my interpretation, is copy paste is the worst enemy of the program. And so there's this strange convention in C++ and subsequent languages that when you want to create an object, you use the name of the class, which is automatic, which is by default, or compulsorily overloaded as if it were a procedure name. There's no reason for that convention. It conflicts with cases like this one. Actually, I do not know how to have a class point with two constructors, Cartesian set and polar set, with the same signature, without doing it in a strange way, adding an extra argument which says which one you want. So it just doesn't work. And this becomes even worse with the even more bizarre convention of C++ and its subsequent languages, Java, C# and such, that ontogeny repeats phylogeny. So this expression, ontogeny repeats phylogeny, it's kind of awkward theory that was popular for not very long, for a few years in biology, that the evolution of the individual reproduces the evolution of the species. So when you're a fetus, you start being like an amoeba, and then a little later you're like a fish, and then you're like a frog. I mean, I'm simplifying it. So this was long discarded by biologists, but it's what's applied by C++, because automatically in C++, and to a large extent in languages like Java, a constructor of a class automatically invokes the constructors of the parent classes, which is really a very bad idea. So the reason that they did this, of course, is that you realize that if C inherits from B, somehow they thought that you have to create an instance of C first as an instance of B, and then do the C specific stuff. But that is wrong. What they were missing is the notion of class invariant. Okay? Because what I just said, that a C object has to become a B object first, and then a C object. There's no argument for this. There's no reason for that. No reason whatsoever. It's just a figment of someone's imagination. What they were missing is the correct property that any instance of C has to satisfy the invariant of C, and the invariant of C includes the invariant of B. And that's what inheritance means, deep down. C inherits from B means that any instance of C must also be acceptable as an instance of B polymorphically. So any consistency constraint that applies to instances of B also has to apply to instances of C. So that's the real underlying reason. But this is something completely different, and it does not need to be achieved by creating you first and as an amoeba, then as a fish, then as a frog, and so on. So now the place where it becomes an absolute disaster is C++, because you have the attempted multiple inheritance. And of course, in multiple inheritance, you can have several parents. And so in what order are the constructors of the parents going to be executed in such a case? And of course, of the parents, and so on. Well, this is a really good question. And the C++ has a very clever answer, which I think about 6 people in the world understand, maybe 7. Okay, sorry, I'm not one of them. I tried to understand at some point. I gave up. But there's no need for that kind of complication. Absolutely not. And so the result is that a multiple inheritance got this reputation of something that is messy, complex, bad for your teeth, and so on, which has absolutely no reason, which has absolutely no justification. The only reason is this misunderstanding of inheritance by C++. So let me use the opportunity to talk a little bit about multiple inheritance as it's done in Eiffel. So here I switch to some slides that I have. Sorry, I have to go back a little bit. Yeah, multiple inheritance is a very natural concept to combine abstractions. You know, a dining car is a restaurant. It has all the features of restaurants, and it's a train car, and so on. So, okay. Multiple inheritance is not the works of the devil. It is not bad for your teeth. So there are interesting cases to which I'm not going right now because I don't have the time, which is the so-called diamond structure, repeated inheritance, but that is solved very easily. It doesn't need to be complicated. There's a very simple rule in Eiffel for this. So here's an example of multiple inheritance, the notion of composite figure. So, we have simple figures, and we can, this is, for example, in PowerPoint, I can take a group of figures and decide from now on that, so I have an icon here, group, and from now on, it's a single object, right? Single figure. So we all know this. We're all used to this in, I'm sorry, I shouldn't have done this. Yeah. If I mess up with my own presentation. So how do we define this notion of composite figure? Very elegant notion. Well, this is a composite figure, okay. I hope you can admire my PowerPoint skills. Okay, so we define a composite figure, which is a wheel, and then if we have composite figures, it's a recursive notion, right? I have a composite, I can have a composite of composites. So how do we define this? Well, what's a composite figure? It's a figure. It has all the attributes, all the features of figures. You can display it, you can hide it. It has a center of gravity and so on. But it's also a list of figures, and it has all the features of lists. You can add something to it, you can remove something to it, you can ask how many elements it has, and so on. So a perfectly legitimate and very useful notion of or example of application of multiple inheritance. And that's the way you're going to write it in Eiffel. There's no complication whatsoever. And if you don't have it, then you're in real trouble, as any Eiffel programmer who has been forced to program, for example, in Java can testify. Once you get used to this, you find everything else really bizarre and constraining. So the one thing that I think is important to explain is why interfaces as they exist in Java do not solve the problem. Okay? Because typically what people say, well, it doesn't matter because in Java I can use multiple inheritance not from classes, but from interfaces. So what's an interface? It's a class without implementation. It's like a class without implementation, except that unfortunately there's no notion of contract, so you cannot even specify what the operations are doing. So it's kind of an abstraction without any implementation whatsoever. But it's not good enough. Okay? So a typical example, which comes from the library, is the notion of comparable and numeric. And so comparable is the implementation or the embodiment of the notion of total order. So comparable is a class with operations like less than or equal, greater than or equal. So it corresponds to a total order, to a set equipped with a total order. Then you have a class called numeric, which is the embodiment of the notion of a commutative ring. So it's an operation where it's a set of objects, a class of objects representing a set where objects can be applied, operations plus, minus, multiplication, division, and there's a 0, there's a 1, and so on. So these are abstract concepts. And we have things that are comparable but not numeric. Like, for example, string. You can compare two strings, but you can also concatenate them, which is a kind of addition, but there's no multiplication of strings. So string should inherit from comparable, but not from numeric. Then you have things that are numeric but not comparable. Complex numbers are numeric, but there's no meaningful total order relation on complex numbers. So this to say that these two things, comparable and numeric, they have to be separate abstractions. But then you have things like integer, which is comparable and numeric, and real, which is also comparable and numeric. So it's a typical case of multiple inheritance. Now, your typical Java programmer or Java enthusiast would say at this point, no big deal. They should be. We can have multiple inheritance from interfaces. But if you look into it, it doesn't work. Let's take comparable, for example. Okay. Let me write the class comparable. It's Eiffel syntax, but you know, I could do it in Java as well. There's nothing Eiffel specific there. And so, okay, so deferred means abstract, right? Not implemented. The difference between Java and Eiffel here is that Java does not have this notion of a class where well, it has interfaces, it has abstract classes, but here I'm going to write a class. There's no special notion of class. It's just that the class can be deferred, meaning it's not fully implemented. But if it's deferred, it can still have non-deferred, also known as effective features. So it can have a mix of features that are deferred, meaning specified but not implemented, and features that are effective, meaning implemented. So we start with less. Okay, less. I'm declaring it as alias less than, so it makes it possible to call it to call things. I don't know if I have. No, I don't have a slide which says it, but calling it alias less means that instead of writing a.less of b in parentheses, I can just use the usual infix syntax a less than b. Okay, so less is deferred. So okay, the Java fan at this point says fine. You see, it's an interface, right? There's nothing implemented. But next comes less equal, and the point is that we don't want less or equal to be deferred, right? Because once we have defined less than, and assuming we have equality, of course, then less than or equal is not open anymore. It's completely defined. It's, you know, a is less than b or equal. A is less than or equal to b if either a is less than b or a is equal to b. And same thing for greater than. You know, a is less than b if b is greater than a, or the other, I should say a is greater than b if and only if b is greater than a, and same thing for greater than or equal. So we want to have this absolutely fundamental technique of well understood object technology, which is that we fill implementations little by little. We have classes which are partially abstract, in Eiffel terms, partially deferred, and partially implemented. And if we don't do this, if we make this an interface, then it means that every descendant, every class that implements this interface has to provide not only less than, which is inevitable because each kind of comparable class will have its own version of less than, but also has to redefine less than or equal, and to declare again less than or equal, greater than. And this is terrible, first because the code is going to be the same. So we have one other example of this horrible copy-paste form of programming, but also it's error prone, right? Because nothing forces the descendants to write these routines in this way, because we didn't fix it at the top level. On top of that, if I were doing this in Eiffel, I would have contracts and I would have preconditions and postconditions and maybe a class invariant which specifies the property. So at least as to limit how much a descendant of the class can mess up, but in Java I cannot even do that. So this is really a result of what I would call total misunderstanding of object-oriented concepts. Let me just sketch some of the other things, and then I need another 10 minutes. I think I was given an hour, so I'll stick with it within that hour. Let me mention in much less detail things that have been completely left out of the mainstream object-oriented languages, and to me are critical. So one of them is void safety. I have some stuff about this. So void safety is about what Tony Hoare calls his billion-dollar mistake, which is null pointer dereferencing. Okay, so if you look at the database of the common vulnerabilities and exposures to security, you see that a significant part of the major security attacks that you find in the field are due to null pointer dereferencing. And so in an object-oriented context, what this means is that when I apply the basic operation of object-oriented programming, which is take an object denoted by a certain reference name X and apply a certain operation to it with certain arguments which don't play a role in this part of the discussion, when you apply this operation, you need to make sure that X, which typically denotes a reference, actually goes to an object. But X could be null or void, the same thing. And if so, all hell breaks loose. So this is kind of the sword of Damocles that hangs over the execution of every object-oriented program, and in terms of widely implemented languages, until Eiffel came with a solution, it was there, and it's still there in other mainstream object-oriented languages. So just to be objective, to be clear about this, when I said when Eiffel came up with a solution, we did not invent the entire solution by ourselves. We took inspiration from research in experimental languages. The Eiffel mechanism is original; it's sui generis. But it had influences which we openly recognize, but it's still unique in terms of mainstream languages. And so in Eiffel today, and for the past 10 years, it's not new anymore, Eiffel is void safe, meaning that if your program passes compilation, if it's accepted by the compiler, then you have the guarantee that this is not going to happen, that you're not going to have a void reference call or the equivalent of a null pointer dereferencing. This has actually been proved mathematically by a PhD thesis, and it took many years to get this right. And let me just sketch how the solution works. I think it's this is the only slide that I'm going to show. I mean, it could be a talk by itself. First, there is some static analysis on the part of the compiler. That is to say, it can certify that some cases are safe, that they're not going to produce any null pointer dereferencing. So we don't need to demand anything of the programmer. In some cases, if you say if X not equal to void, then X.F, you're okay. In some cases, because if we are in a multi-threading context and X is a field, that what I just said is actually not true. So there has to be some conditions. Either you don't have multi-threading, or you have a safe form of concurrency, or X is, for example, a local variable. So there's a certain number of what we call certified attachment patterns, which are guaranteed stamped patterns of use, which promise that they will not cause a void code, a null pointer dereferencing. Then there is a mechanism, a safe mechanism to test for nullness in a guaranteed way. Then there's the notion of attached types. You can define a type as being attached, meaning that the variables of that type are never going to be null. And then, yeah, so there, it turns out that the key issue, the most delicate issue, the one that took really several years to get right, is initialization. And then there's a special rule for generic parameters, which raise some particular problems. So, I should say in this respect that it took about, one afternoon to get the basic idea right. And it took about 10 years to get the engineering right. Maybe not quite 10, but 7 or 8 years to get the engineering details right. The devil is often in the details. Last point I wanted to mention is concurrency. So again, I can just give you a glimpse here. Where's my? Yeah, it's here. So, most people, when they program concurrent applications, program like this, right? This is actually from a very well-known textbook. It's the dining philosopher problem. It's absolutely, it's unacceptable in 2022 to have concurrency at the level of programming semaphores and trying to understand, is this going to happen first, or this could get in between, or no, what is suddenly in a very short interval the other guy gets in. It's just completely unacceptable. So this is the dining philosopher example. In Eiffel, this is how you write it. The philosopher lives repeatedly, and every step of the life of the philosopher thinks, and then eat, having grabbed his or her left and right forks. And eat says, do whatever you do, you pick your left fork. So that's it, okay? It is guaranteed, thread safe, of course, data race safe, and everything. And of course, deadlock free in this case. So to give you just another example, again, I'm kind of condensing like 20 talks into one, but there's this example that we wrote for a little robot, and if this was based on rules from a biology journal about hexapods. You have this group of legs. The green legs and the red legs move together. So there are rules like protraction begins only if the partner legs are down. Partner means the partner of the green legs are the red legs, and conversely, depressed legs only if the partner legs have been retracted, and begin retraction with partner legs up. If I had a little more time, I would give you a video of this thing working, because we actually built it. And the way we programmed it in using threads, in Java or C. And again, it's extremely low level. It's impossible to understand. And the way you write it in Scoop, which is the concurrent version of Eiffel, the concurrent mechanism of Eiffel, it's part of Eiffel. It's what you use for concurrent mechanism is that you directly translate those rules that I just mentioned into preconditions, yeah, it's just direct implementation of the edges. So let me mention one more thing, and then I'll stop very quickly. It's a blog that I wrote just a couple of weeks ago in the blog of the communication this year, because I do want to say a word about design by contract. So design by contract is the obvious rule. I mean, some people make a big fuss about it. The question to me is, how could one ever write even a single routine, a single class without these techniques? To me, this is why I call this this particular blog mental self-check, because in many insane asylums, people inside the asylums think that the rest of the world is crazy. And so I'm inside the asylum and I'm asking myself, is the rest of the world crazy for not using these techniques? And I think the rest of the world is crazy, but of course, the rest of the world, which is a big majority, thinks otherwise. But so this is an example. Here is the link for those who want to read it. It's very easy to find. It's on the Communication of the ACM blog. So it's a program I'm writing. It's a pretty contorted, I mean, not contorted, pretty sophisticated program. It has very sophisticated data structures with references all over the place and redundancy and so on. And so I have a class invariant which has this. It's written in more detail here. But yeah, and by the way, you can write this exactly the way it is in Eiffel, right? With these Unicode for all, and if you want, you don't have to. But anyway, so you can see that it's a quantified expression at 3 levels. For all t in the list triple successors, or maybe it's a hash table. Now the list for all L in T. T is itself a sophisticated structure. For all P in that list, L is a list. So you have, I think something like a hash table with a hash table of hash tables of lists, then some property. So this is the only way I know to manage these things properly, because the data structures are complex, and if I don't write the consistency conditions between the various parts, then I'm sure to mess up. And then, of course, when we execute this, it's going to be monitored at runtime. So when I run my program, there's literally hundreds of thousands of these individual equalities here that are going to be checked. And so when this runs, it's not like a proof. They're also proof tools, but they're not as advanced. For day-to-day programming, it's still dynamic, it's still tests. But so it's not a proof. But when I have such intricate conditions that first help me write the program correctly, and second help me find the bugs, when you have these hundreds of thousands of individual properties that are checked and pass the test, well, I'm pretty sure I am pretty comfortable with my code, as opposed to running a test or 1,000 tests or 1,000,000 tests, which doesn't really tell me anything about whether my program is really correct. I mean, I know that it passes the tests, but what else do I know? So why anyone would not use these techniques passes my understanding. So that's why I'm inside the asylum rather than outside. So there would be more examples to cover, but basically what I've tried to convey is that if you go back to the source of object technology, these ideas of information hiding, data abstraction, and such, then if you apply them properly, you end up with something like Eiffel, but it also means that you're in a much better situation to achieve the advertised benefits of object technology.